Hello students, and welcome to section 3-2, linear functions. Example 1. Evaluate functions in function notation. How can you represent a function rule? Write the equation y equals 5x plus 1 using function notation. Remember that a function is a rule that takes an input or an element in the domain and maps it to an output or an element in the range. Function notation is a method for writing variables as a function of other variables. The variable y becomes a function of x, meaning the variable x is used to find the value of y. This helps distinguish between different functions. You can use the relationship between variables to solve problems and make predictions. So we're going to go ahead and take a look. It's a nice visual, I think, of which the element in the domain, call it x, is inputted into this system, or function technically, if you will, as such, where it in fact starts off as a equation or expression. I'm going to adjust this because there's a typo. This should be 5x plus 1. And then as that x continues through the function, and in other words, plugging in values for x, you get outputs or elements in the range as a result. F of x is another way to describe this, and that's literally how I would like you to say it. F of x, and that's how it's read, and that's your y value as we disguised or described earlier. It is disguised in a sense as a different variable, but technically f of x is the same as y. The function f is defined in function notation, we say, by f of x equals 5x plus 1. What is the value of g of x? What is the value of g of x equals 5x plus 1 when x equals 3? So notationally, g of x equals 5x plus 1. For x equals 3, we're going to evaluate, but you're going to input 3, substitute the input 3 for every instance of x in the function. So 3 goes in, and as you can see, I'm plugging it in for x, and I'll go ahead and readjust this sign again such that it's 5 times 3 plus 1. And that math lends itself to simply, well, g of 3 now equals 16. Function notation can use letters other than f. Other commonly used letters are g and h. So g of x equals 5x plus 1. When you evaluate it at or for 3, same thing, g of 3, 5 times 3 plus 1, you get an output or range value there of 16. Let's move on. Write a linear function rule. The cost to make 5 or 4 bracelets is shown in the table. How can you determine the cost to make any number of bracelets? Okay, so here's the table. Here's step 1 first. It says examine the relationship between the values in the table. So you can see here that we've got some things to designate here, particularly where you've got your x's, the number of bracelets, versus y, the cost. So 1, 2, 3, 4, and as these x values increase by 1, what happens to your y's? Well, the y's increase. It appears, as you can see, 17, 32, 47, and so on, 62. The constant rate, in other words, the change that this is going up at, or the rate of change that this is going up at, or the slope, you can also argue, is simply 15. The relationship, therefore, is linear. Very important to highlight as we go through this, how the two kind of connect. So let's move on. We do have obviously more to discuss here, so we can see in step 2 it says write a function using slope-intercept. That form in particular for the rule. F of x instead of y is equal to mx plus b. F of x equals 15x plus b. As I described earlier, m, or your constant rate of change of 15, is obviously being what we're looking at it, and it's being applied in such a way where it is your rise over your run, or change in y's over change in x's. Step 3, find the value of b. We've done this before. When you know the slope, and let's say if you know a point, you can pick a point, let's say 1, 17, which they've done here for you. X is 1 when y is 17. And you can solve for b. 15 times 1. Subtract 15 from both sides. 17 minus 15, of course, is 2. So your answer, therefore, for b is just 2. You can use the function f of x equals 15x plus 2. And again, you can argue that as the same as y equals 15x plus 2 to determine the cost to make any number of bracelets. The function f of x equals 15x plus 2 is a linear function because the rule 15x plus 2 is the same as the rule of the linear equation. Like I said earlier, y equals 15x plus 2. And of course, you can graph if you'd like to take a look and see how this in fact is a linear function. We're not going to be graphing, at least on that problem, but certainly later you'll need to know how to make those connections. Okay, example 3. Analyze a linear function. Tamika records the outside temperature at 6 a.m. The outside temperature increases by 2 degrees Fahrenheit every hour for the next 6 hours. If the temperature continues to increase at the same rate, what will the temperature be at 2 p.m.? So we're going to go ahead and devise our plan looking at step 1 to write a function that models the situation. And again, as we denoted in the directions, there is a 2 degree Fahrenheit increase each hour. So that is a rate. If you think about it in terms of slope, we'll make that connection as well. But keep that in mind. There is a change of 2 degrees per hour. It's an increase. All right, if we continue on here, and I'm going to have to move that. The equation f of x equals 2, again, an increase of 2, so 2x, there's your slope, 2 degrees Fahrenheit per hour times x, and then minus 3. Where does the minus 3 come in? If you kind of denote here where we're starting, okay, minus 3, then from there, of course, it's going to go up. So let's keep going. That's your y-intercept, obviously. Sketch the graph of the function, so let's take a look. And we got all these interesting parts to still kind of highlight here. I know it's done for you, but look, the y-intercept of -3, that's the starting point. And over the course of time, obviously the temperature goes up. How does it go up? Well, from -3 we go up 2. Okay, actually -3, 1, 2, and then right 1. Up 2, right 1, and so on and so forth. You go up 2, right 1 until you obviously can formulate your nice curve or your nice line. Moving on. Step 3, find the value of y when x equals 8. Simply, you can plug in 8. There it is. Y equals 2 times 8 minus 3. That's 16 minus 3, or 13 degrees. Assuming the temperature continues to increase at the same rate, the temperature at 2 p.m. will be what? Well, 13 degrees Fahrenheit. The graph of f of x equals 2x minus 3 is a line. A linear function, as you know, is a function whose graph is a line, and you can see that obviously in the picture. Y-intercept of -3 again with a slope of 2. Okay, and if you wanted to kind of see here also at 8, what is the y-coordinate, you can see that 8, 13 is in fact the point on the line. Part B. Does using a linear function realistically represent the temperature for the domain of 0 less than x less than 24, and explain? Well, the realistic idea here plays into things which we've seen in the past where, again, it says the graph of the function has a slope of 2, which represents the temperature rising 2 degrees Fahrenheit each hour. However, when the sun sets, it is unlikely that the temperature will continue to rise. The linear function is realistic for only a portion of the day. Of course, the temperature will in fact, go down once the sun sets. Moving on, example 4. So use linear functions to solve problems. A chairlift starts 0.5 miles above the base of a mountain and travels up the mountain at a constant speed. How far from the base of the mountain is the chairlift after 10 minutes? So 0.5 miles from the base, you see that denotation below. And then the chairlift, it says, travels 6 miles per hour. There's a rate. It takes 15 minutes to reach the top. Let's take a look. Let's formulate. Write a linear function to represent the distance the chairlift travels from the base of the mountain. Let t equal time in minutes. The speed of the chairlift is in miles per hour, so convert the speed to miles per minute. Just an added little conversion step, as you can see. So 6 miles per hour, there's a rate again. Multiply times 1 hour and 60 minutes, or 60 minutes in an hour, of course. And as it turns out, we'll be able to cancel our units as such. Hours divide out. So you can then multiply across 60 times 1 divided by, or 6 times 1, pardon, divided by 60, which is 0.1 miles per minute. The speed of the chairlift is in miles per hour again, so we have to convert. If we continue, the distance traveled equals the rate of the chairlift times the time traveling, plus the distance from the base. As such, d of t is equal to 0.1, which we just ended up with, of course, from here, miles per minute, times t. T is unknown. We don't know how long it's going to take total, plus 0.5 miles from the base. Continuing on. The distance of the chairlift from the base of the mountain at any time is represented by the linear function d of t equals 0.1t plus 0.5. Evaluate the function for t equals 10. D of t equals 0.1 times 10 plus 0.5. 0.1 times 10 plus 0.5. The math ends up looking like this, 1 plus 0.5, and the graph does, as you can see off to the right, take shape. 1.5 is the resulting y if you plug in 10 for t. So let's look at the graph for a moment. I'm going to do an interpretation as well at the same time, but in the graph you can see the y-intercept is 0.5, the slope is 0.1. So if you start at 0.5 and go up 0.1, right 1, actually these are going up by 2, so up 0.1, right 1 would be here, and so on and so forth. Rise over run should take you all the way to this point, which again, as we solved for by plugging it into this equation, d of 10 ended up being what? 10 comma 1.5. And that's the distance in miles. So after 10 minutes, the chairlift will be 1.5 miles up the mountainside. Okay, so that full analysis and interpretation hopefully makes sense in context. Please also, if you could, take a look at the try it just for further analysis.